Okay, we're going to look at part 2 of our final exam review. Most of these questions come from Module 7 in our course. So a lot of the analytic trig and things like that will be in this section. So attached to your review, you'll find a formula sheet that has all of our identities and stuff that we use. So if I reference those are all in that formula sheet. So the first one says, simplify the expression 1 minus cosine tangent sine. So I want to try to make it simpler. Now, if we recall, whenever we're trying to simplify identities and such, we try to write everything in terms of sine and cosine. So if I do that, I can make this 1 minus cosine. But if you remember, tangent is sine over cosine. And again, that's one of our identities you can see on your reference page. So 1 minus cosine times sine over cosine times sine x. So the nice thing is we have a cosine on the top and bottom which will cancel out. So what we end up with is 1 minus sine squared x. But there are two very important Pythagorean identity rewrites, and I'll just reference them over here. If you remember, cosine squared x is 1 minus sine squared x, which we'll use in this one, and sine squared x equals 1 minus cosine squared x. These are identities that aren't really on your sheet, but really they're just rewrites of the general Pythagorean identity sine squared plus cosine squared equals 1. So they're just written a little differently. So obviously in this case we can take advantage of this one, which says 1 minus sine squared x is simply cosine squared. So I can simplify this down to cosine squared x. So I've taken this big, long kind of expression and I've simplified it down to something very simple. Okay, let's look at number 2. Number 2 says, verify the trig identity 1 over sine y minus 1 over cosine y equals cosecant y secant y, parenthesis cosine y minus sine y. So kind of a lot going on here. So to verification, we're going to try to start on one side and work our way to the other side. Now, there is no right answer, but I'm going to start on this left side or right side because there seems to be more stuff going on. And I notice I have these parentheses around these two. So that's going to be key. So since I have these things in front, I can actually distribute these to both of these terms. So I can actually rewrite this as cosecant y secant y times the cosine of y minus, again, the cosecant of y times the secant of y times the sine of y. Now that's just a simple distribution and it kind of gets rid of that big set of parentheses and leaves me with this I can kind of work with. So again, in most identities I'm going to try to change them to sine and cosine. So if I look at my formula sheet, I know cosecant is 1 over sine y. Secant y is 1 over cosine y times cosine y. And again, minus 1 over sine y times 1 over cosine y times sine y. Now again, I didn't do anything fancy. I distributed. I changed them to sine and cosine. And now I'll cancel out what I can. So I can cancel out a cosine there and a sine there. So I'm left with 1 minus sine y minus 1 minus cosine y, which is exactly where I wanted to get to. So we knew where we were trying to aim for. We knew what we wanted to end with. We just had to kind of show the steps to progress from one side to the other. Now number 3 says given sine of theta equals 1/3 with theta in quadrant 2 and tan beta with beta in quadrant 4, find cosine of theta minus beta. So if I look at my formula sheet, I do have a formula for cosine of two angles subtracted. It says the cosine of two angles subtracted, the first angle theta, the second angle beta, is equal to cosine theta cosine beta plus, it's the opposite sign, sine theta, sine beta. So really the crux of this problem is really finding these four values and simplifying our answer. Now I know what the sine of theta is because it tells me. Sine of theta is 1/3. And then it tells me sine of beta is -7/4, but I don't really need that. So somehow I have to figure out how to find sine beta, cosine theta, and cosine beta. So what we'll do is we will take our axis and we will actually draw two triangles for each of these. So I'll draw a triangle for this one. So it says in quadrant 2 I have a triangle. So I'm going to draw a little triangle there with a theta there. Now it says sine is 1/3. Now sine is the opposite over the hypotenuse. So the opposite of theta is 1. The hypotenuse is 3. I can then use the Pythagorean Theorem to find this side of x, which I know will be negative because it's going in that direction. So 3 squared equals 1 squared plus x squared. So that's 9 equals 1 plus x squared. I'll subtract 1, so 8 equals x squared. Take the square root, so x is the square root of 8. So in this case, x is the square root of negative square root of 8. Now why this is beneficial for us is now that I have the full triangle for theta, I can find out what cosine theta is. Because cosine is the adjacent over the hypotenuse. So it's negative square root of 8 over 3. So now I'll do a very similar thing for the other triangle. I'll do one for triangle beta. Now it says triangle beta, tan equals -7/4 with beta in quadrant 4. So I'll draw it down here in quadrant 4. So I know this is positive direction, this is negative direction. And there's our beta. So we know the tangent of beta is -7/4. Well, that has to be opposite over adjacent, because tangent is opposite over adjacent. So the opposite side is -7, and the adjacent side is 4. I can again go and find my hypotenuse using the same thing. So we'll find this hypotenuse, c. So hypotenuse always goes by itself, so c squared equals 4 squared plus -7 squared. So c squared equals 16 plus 49. 16 and 49 is 65. So c squared equals 65. Taking the square root says this hypotenuse is going to be square root of 65. So I set up two triangles, one for theta, one for beta, and that'll allow me to get all these different things. So now let's find what is the cosine of beta. Now cosine is the adjacent over the hypotenuse. So that's 4 over the square root of 65. So that'll go here. 4 over the square root of 65. And sine is the opposite over hypotenuse. So that's -7 over square root of 65. So -7 over square root of 65. So now I will try to simplify this. I'll just multiply. So this will be -4 square root of 8 over 3 square root of 65 plus -7 over 3 square root of 65. And that's just multiplying straight across. So if I add those over the common denominator, I get 4 square root of 8 minus 7 over 3 square root of 65. Now this problem was done on a difference, the cosine of two angles. You could also do it on the half angle or the double angle or really any formula you see on your formula sheet. We could do a very similar logic. Okay, the next couple problems, 4, 5, 6, and 7, are all going to kind of use our identities, but they will also use our unit circle. So it would be a good idea to find your unit circle, or go find one online that you can use for this. So this says find the exact value of 15. Now 15 is not on our unit circle, because typically the things on our unit circle are 30, 45, 60, and increments of those. So we have to use one of our identities to find 15. And there are several that you could do, but I'm going to do a subtraction identity. So we know if we have two angles subtracted, sine of x minus y, we know that I can write that as sine x cosine y minus cosine x sine y. And that again is just one of the identities from your sheet. So if I think of two angles that subtract to 15 that are one of these nice angles up here, then really the sine of 15 is the sine of 45 degrees minus 30 degrees. So in reference to our formula, our 45 is kind of our x and our 30 is kind of our y. So when we substitute into the formula, we just basically substitute those in. So if we first look at it, so this will, sine of 45 minus 30 will be the sine of 45, which we will get from the unit circle, times the cosine of 30, which we can get from the unit circle, minus cosine of 45, same thing, unit circle, times the sine of 30. So if I go to my unit circle, the sine of 45, remember it's the y-coordinate for sine, is square root of 2 over 2. If I go to cosine of 30, now that's the x-coordinate, I get square root of 3 over 2. If I look what the cosine of 45 is, I get square root of 2 over 2 as well. And the sine of 30, which is the y-coordinate, I'm going to get 1/2. So now if I multiply these across like I did in the last problem, I get square root of 6 over 4 minus the square root of 2 over 4, which I can simply write as the square root of 6 minus the square root of 2 all over 4. So the sine of 15, the exact value is the square root of 6 minus the square root of 2 all over 4. Okay, let's look at number 5. Number 5 says, what is the exact value of the cosine of 67.5? Now I can't think of two numbers that add or subtract to give me 67.5, but we also have an angle formula that will cut it in half. So we have what's called the half angle formula. Now the half angle formula for cosine says cosine of alpha over 2, we'll use the angle alpha, doesn't really matter, is plus or minus the square root of 1 plus cosine of alpha over 2. So can we think of a number that would be cut in half to get 67.5? Well, if I take 67.5 and I multiply it by 2, I get 135. So 135 cut in half is 67.5. So I can use this formula just using 135 as my alpha. So the cosine of 15 is going to be equal to the square root. It is positive because 67.5 is in quadrant 1 and everything is positive in quadrant 1. 1 plus the cosine of 135 over 2. Now cosine of 135 is on my unit circle. If I look it up, the cosine of 135 is negative square root of 2 over 2. So this is minus square root of 2 over 2 all over 2. Now one thing we do to simplify this, if you recall, we'll multiply everything by 2 to get rid of this fraction. So our simplified version will be square root of 2 minus the square root of 2 all over 4. But if I want to take it a step further, the square root of 4 is just 2. So I can write this as the square root of 2 minus the square root of 2 all over 2. So the exact value of cosine of 67.5, I'm not sure why I wrote 15 there, 67.5, pardon me, is square root of 2 minus square root of 2 all over 2. So let's look at our next problem where we were trying to solve an equation on a certain interval. So this says 2 sine theta plus 1 equals 0. We're trying to find all the solutions in the interval 0 to 360, which is just our unit circle. Remember, 0 to 360 or 0 to 2 pi is just simply the unit circle. Okay? So we're trying to find what angles of theta would make this true. So the first thing I'd want to do is I would want to try to get my trig value function by itself. So I'm going to try to get, in this case, the sine by itself. So I will subtract 1 from both sides. So 2 sine theta equals negative 1. And then I will divide both sides by 2. So sine theta equals negative half. So now all I have to do is I want to look where on the unit circle has a sine value of negative half. Now since sine is the y-coordinate, I'm just looking on my unit circle for what angle on the unit circle has a y-coordinate of negative half. So if I look here and look what has negative half for its y value, that would be at, first angle is 210, so theta is 210, and again this is just the angle on the unit circle that has the y-coordinate of negative half, and the other one appears to be at 330. So those are the two angles on the unit circle that would have a sine value of negative half, thus would make this equation true. So let's look at the last one. The last one says solve the equation cosine squared minus 2 cosine minus 3 on the interval 0 to 360. Now this one's obviously different because it has squares and things like that. So the first thing I'd want to do is, if you recall, we try to factor this. So instead of looking for cosines, let's just write it, instead of cosines, let's just write it in terms of u. So everywhere I saw a cosine of x, I replaced it with a u. And the benefit of this makes it a little easier to factor. So if I factor this, u and u, I'm looking for two numbers that multiply to negative 3, add to negative 2. That would be minus 3 and positive 1. So now I've got it factored into two linear factors. So I can replace my cosine in for u. So I'll get cosine x minus 3, cosine x plus 1 equals 0. So now I can set these both equal to 0. So cosine x minus 3 equals 0. Cosine x plus 1 equals 0. So adding 3 to the first one will give me cosine x equals 3. And the second one will give me cosine x equal negative 1. Now looking on the unit circle, we know cosine never is bigger than 1 or less than negative 1. So this one is not going to have an answer. So really all I'm looking for is trying to figure out where cosine is equal to negative 1. And this is actually on our unit circle. It is 180 degrees. And that's the only place. If it wasn't on our unit circle, and if you didn't even want to use the unit circle in this case, you could just use the inverse cosine. So if I did x equal to inverse cosine of negative 1, it would also give me this same 180. So hopefully these problems were beneficial as you review for your final. Let me know if you have any questions on any of the problems.